So fault systems, they can either be thin-skinned or thick-skinned, and no, they won't really get their feelings hurt. They're rock. They don't care. Thin-skinned fault system is in the shallow sedimentary rocks, shallow depth faults near the surface of the earth. Thick-skinned or thick fault systems are ones that go into the basement rock, into the crystalline rock. They go much deeper. Some of the other terms we've seen before. We've seen them in joints, we've seen them in fractures, we've seen them in other things. Parallel, really basic term. We know what parallel lines are, we know what parallel beds are. Parallel faults are simply faults that are approximately parallel to each other. So in this case, these are all faults. There are 3 faults here. Anastomosing, braided, just like an anastomosing stream is a braided stream. Anastomosing faults are this kind of braided look to faults. They're parallel and subparallel, but they keep intersecting and crossing and splitting apart. En echelon, in series. So we have some en echelon faults or en echelon joints along a fault. Now this is a new term called relay. It's a bunch of roughly parallel faults, but they're all offset from each other, and so if these were all, say, right lateral transform faults, the area near the top of the image has moved to the right, the area towards the bottom of the image has moved to the left, but there's not one large fault. Each of these shorter faults has released some of that stress and allowed some of that motion, and the net effect is that the top moves right and the bottom moves left. So this is called relay. A relay zone is an area with a bunch of faults like this that allow for the overall sense of motion. Conjugate, just like in joints, conjugate joints, you can have conjugate faults. Then we can have random faults. They're not following a regular pattern like those conjugate ones or the parallel ones. They're just in all different directions. We can have normal fault systems with listric faults, like in the top block there, and we can have normal faults without any listric faults that are all straight or approximately straight faults, creating a Horst and Graben system. We have a large area in the US, down in the southwest, full of Horst and Grabens. It's the basin and range area. The basins are the Grabens, they're the low parts, and the ranges are the Horsts, the high parts. Now, I always do this with a visual when I'm in person. You guys are just going to have to imagine. This is my trick for remembering the difference between a Horst and a Graben. The Horst looks like you could be a cowboy, throw your leg over, and ride the Horst like a horse. Put a saddle on it and giddy up, away you go. You can ride the Horst. The Graben, some troll in the ground has reached up and grabbed the ground and pulled it down. In the tilted listric fault area, we get a bunch of half grabens, where one side of it has been pulled down and one side of it's still sticking up, and they're all tilted. Those are called half grabens, because only half of the block got pulled down. In this case, the left side of each of those blocks. And what do these have in common? They are both tensional areas. The normal listric faults and the basic normal faults are both tensional. So we have stretching, pulling to the sides. We see these in rifts, we see these in passive margins, and we see these in mid-ocean ridges. On the other hand, the opposite of that, of course, is the reverse fault system. So the opposite of the normal fault system is a reverse fault system. This is where we have convergent plate boundaries and collisional origins. These give us things like fold thrust belts and imbricate fans. These are compressional stresses. So we're pushing in from the sides and creating these faults. Sometimes we have some ramps and some flats, and then we can have a series of ramps and we get this duplex system. Very, very common are these things called flower structures. This is always in a transform boundary, so a strike-slip fault like the San Andreas fault, and we get a flower system. It looks like a flower if you have a big cutaway view, and you can see this little flower in the middle here. And here we have the circle with a dot indicating coming out of the page, and the circle with an X indicating going into the page, reinforced by these two arrows up on the top of the map or a block. And within the flower itself, you can see there's uplift, and that's why they're little hills. Now, the reason this happens is because reality is our rocks are not perfect homogeneous things that are going to create little blocks like we see on the right. Those are oversimplifications. In reality, as those two blocks slide past each other, the fault doesn't stay perfectly straight because the rock is not perfectly homogeneous. The faults curve, creating transtension and transpression, so we have some uplift and some sag, kind of alternating, creating this anastomosing fault array. And so from the top we see the anastomosing structure, from the side we see a flower structure. So I've just spent over an hour talking about faults, but outside of this class and the test coming up, why do we care? What does it matter? Why would anybody study faults? Well, sometimes they are great at helping us find resources. We can find coal, we can find oil, we can find ores, we can find groundwater. The reason for finding oil, for example, is that a fault can either create a trap, a place that collects the oil that we can then drill into, or it can create a release and the oil comes up to the surface and helps us find it. With coal, it can expose a coal bed, or one edge of it, and then we know to dig into that area to find more and more coal. With groundwater, it can show us, let us tap into an aquifer or tell us that there is an aquifer to tap into. And again, with ores, it's just like with coal. Expose part of it, then we know to follow those beds and those veins to get more and more ore. Faults also affect where we want to build. We have to worry about earthquakes. We have to worry about slope stability. It becomes very important as an engineer to pay attention to faults. What kind of structure you choose to build next to the San Andreas Fault versus in Grand Forks, North Dakota will be different if you're paying attention, because right beside the San Andreas Fault you're going to have earthquakes because of that fault that you're not going to have if you're building in Grand Forks, North Dakota. We don't have a big transform fault here, therefore we're not going to have constant regular earthquakes. They also help with understanding Earth's construction. Sometimes by the simple matter of exposing it on the face of the fault, sometimes because that fault motion gives us an earthquake. Those vibrations get detected throughout the world at different seismic stations and helps us see a picture of the inside of the Earth by turning it into a giant seismic survey. So these faults can tell us lots of things about the Earth. And they can destroy stuff. Faults and the earthquakes caused by movement along a fault are a big, big, big deal. With that, I am done today's lecture. Don't forget about the test coming up this week. This material is on this week's test.